Now, question is, this is about core teaching in engineering, right? And in particular, I will talk about core teaching in physics. Whatever I say remains the same in other subjects also. So, let us now see, and a lot of students say this, and again I want it to be interactive, all right. Let us see why when a student has done 11th and 12th grade of physics, mechanics, electromagnetic theory, and probably whatever at high level you pitch at, they think they are not going to use, right. And also, if when you do it, and this is an experience I have had in a book on mechanics that I wrote, and otherwise students tend to say that you are using too sophisticated an approach, right. For example, I am sure in engineering college, if you have taught a mechanics course, they say use the scalar approach. I do not know what scalar is. I mean, force is a vector, velocity is a vector, acceleration is a vector. So, I do not know what scalar is. So, that is one misconception they have. And when you start using not so much of high level mathematics, but vector calculus, they again start having problems, right. I am sure people in mathematics and physics both have experienced this. How do you handle this? Number one, should we be teaching at this level? Why do we repeat? Why do we repeat what they have done in 11th, 12th, and probably whenever there is a need arises, I should be doing it, I could do it in a course. Why do I go through a rigorous 1 or 2 physics or maths courses? Let us see if it is clear to the teachers, then only I can convey that excitement to the students. Ideas. I am again going to write it up like yesterday, then we will discuss it. And then whatever I have to say, you have to say, I will kind of demonstrate it. Why do you think we have to repeat this physics maths courses again, which they have done in their 12th grade? Or you just go because university and syllabus diya hai karte hain? Yes.
Actually, in engineering course we try to relate your physics and chemistry and mathematics to engineering.
Okay, so let's just write that. Let us just keep writing it. Okay. Again, I will do it like yesterday we did, and so one is that relate science to engineering. Is that what you are saying? So, whatever I teach, I kind of connect it with engineering. Yes, okay. What else?
Physics is the mother of all engineering subjects.
Kitabi line hai, kitabi line hai.
All the subjects are somehow related to physics.
So, we are saying relate science to engineering. Science, okay. So, let us say physics. You are a physics teacher? So, I mean, I would say that each component contributes, but since you said physics, I will also write physics specifically. Okay. Okay. So, that is relating science to engineering. Is that what you are saying? I mean, can I put that in category, or you want to say something more? So, engineering and applications. Let's since you said a word, so let's put it this and. So, that is one purpose, right? What else can you think of, and what else do you think when you teach? बोलिए तो फिर नहीं बोलेंगे तो फिर गड़बड़ी हो जाएगा. कुछ तो बोलिए. I mean, there is nothing wrong. We are just trying to develop ideas. I will add to it now. Okay, I will start adding. So, this is one, but this is something which anybody can say that I want to do it, right. So, I will add a few more, but I would like to know, when you say, it is easy to say that I would like to relate science to engineering. When you teach it, how do you do it? or if any one of you has done it, how do you relate it to engineering? See, so we can say that, like he said, physics is father of engineering, right? So, what we see, what is happening, right? I want to understand it, and by number one, I want to understand it. Number two, I want to see that phenomena, how can it help or hinder in any engineering application. And for that, I have to work hard. I have to see engineering problems, and I have to see what they do, and then relate. Right? That's where your role comes in. So, this is I am still looking for answers. Has any one of you, although you are starting anew, but if you just were to think, give me an example where you would relate it to engineering. And engineering also means that I am talking to students who have just cleared 12th grade. So, they have seen some things around them, but they have not necessarily seen great engineering marvels. So, I have to show them beauty of science in that small engineering whatever they see around, right. So, they start appreciating. See, the one mistake we make in all of us make is try to relate to things which are big, nuclear reactor, aeroplane flying. For all you know, a student who has come from a village near Madhubani, I mean, hasn't seen an aeroplane, right, but he has seen other things, right. So, we relate it to those. Not only that, now what we so this is one part which we must keep in mind in core teaching. I am actually bridging from 12th grade, right. I am making them graduate to a place where they start seeing how it is applied and why it is relevant. But more important, as somebody said, one of you said that when the students have come, they have just studied to clear the exam, most of them. But I would not be that harsh, even if they try to see the perspective, see the science in a bigger way. उनको अकल नहीं होती, maturity नहीं होती. They are not mature enough. 14-15 साल का बच्चा, Hindi you are okay with, right? So, I'll keep. I am taking hint from. He said use English. I am going to use English. So, 14-15 साल के बच्चे को maturity नहीं होती है. उसको आपने बता दिया Newton's first law, second law, third law, लेकिन क्या उसका मतलब है, bigger picture क्या है, he wouldn't understand or she wouldn't understand. So, the second very important point is I want to develop scientific, and that is scientific is scientific. I mean, it applies everywhere, engineering, technology, way of thinking. Very important. If I just take Klepner or Resnick-Halliday solve the problems, I don't. This is where I as a teacher come in. I want to show them bigger picture. I want to show that it's okay to make mistakes when you are solving a bigger problem, but then you also learn how to come out of that mistake, how to analyze. So, scientific way of thinking, what is in parlance is known as scientific temper. Which will involve setting up a problem, right. If I look at, for example, why is it important? Suppose, right, in a structure, the civil engineering structure in a building, some crack has developed, right, and I want to analyze why it happened. Is it cement dried too fast? Is it that the water I used or the ratio I used was not proper? It is formulating a problem. So, setting up, or I would even say formulating. Right. I want an engineer, I want my student when he or she goes out to be able to look at a problem and see why it happened, right. I formulate the problem, and that requires scientific way of thinking. It is not just that I have been given a problem from Halliday Resnick or some coaching book and I solve it. I have to really look at it. Maybe it happened because of this, maybe it happened because of this, maybe it happened. So, I list 4 or 5 possibilities, then scientifically remove one or two of them, and then arrive at the real thing. right. That is called formulating the problem, right. And once I formulate a problem, right, setting up a problem, that is analyze and solve. And when you solve, again, when you do engineering, although we make our laws which are precise, exact, but they are exact because I perform those things in ideal conditions. Real life is not ideal, right. When I say Newton's second law, something in the state of motion remains in motion, yes, there is no other force, but in real life there is friction, right. And how do I take care of that? Similarly, if I am a defense engineer, say designing an artillery, all I would say is, this is a projectile motion parabola, but real life there is friction, drag. Higher the speed, power related to velocity is even higher. I should be able to solve it within some approximation. And finally, what do I want? If I am firing a shell, I don't want it exact 500 meters. It could be 500 because after all a shell makes a the whole of maybe of the radius 5 meters. So, within 5 meters I am okay. So, how to solve the problem in a meaningful way, right? I would not say approximate way, in a meaningful way. I don't like to use the word approximate, because approximate somehow means it may be exact, but no. But even if you solve it approximately, it could be very meaningful. So, meaningful, relevant way. So, develop scientific way of thinking, relate science to engineering and applications, and the two are related. This, and then when you solve the problems, you relate it to engineering problems and how some great minds work to solve a certain problem, right. And then also, although it may come under this, learn to take up some challenging problems. I mean, people don't emphasize this for fun. This you are challenging yourself. Can I solve this tough problem? I mean, whenever you are teaching core, although the kids are here, you should always give some challenging problem. Let them see how much potential they have, right? And it also takes the fear out of them. A lot of students are scared in using, symbols of mathematics, curl, divergence, things like those. Take the fear out of them, make them solve a lot of problems and keep relating to different things. Okay? Now, can you think of anything else? I mean, this is, if I can accomplish this much, I think core I have done, right. Oh, so fourth important thing, although we said that there should be a bridge thing. So, this is application part, but I think if I consciously write it, it will be good. Prepare students to take future later courses that require basic science mathematics. For example, if I am teaching electromagnetic theory, all right, and I do that in my courses, most of the mathematics that is used, and I am going to show it to you, right, is exactly the same that is used in fluid mechanics. If I train them well in electromagnetic theory and try connecting with other fields, fluid mechanics, and flow of heat and things like those, I actually prepare them for heat and mass transfer. Okay, and I have done that in the class, and the students have later come and told me that, sir, that course, that time we thought you were teaching very tough, but later we realized it was very good, because fluid mechanics became very easy, heat and mass transfer became very easy. Okay. So, the core courses play a very important role. Core courses develop scientific way of thinking among the students who have just fresh out of 11th or 12th grade, think they know all the science, then you can ask them, analyze the problem scientifically, right. They also think, why am I studying this? So, you prepare them, you tell them immediate goal that you relate to the subjects later. You also tell them how all this is very relevant to what you do later as an engineer, right. And even some things, if I give you a challenging problem, it may not look relevant even to me today as an instructor, but later you may find it useful. Okay. So, anything else that you can think of? If I am teaching a core course, and most of you are what? Teachers in physics, mathematics, chemistry, physics. You keep these 3-4 goals in mind, your course will become fantastic. Yes. Oh. And to our teachers who are from engineering background, it would also help you if you attend the classes in core course. For example, yesterday he emphasized that you become tutors. You will be able to explain the engineering points much better from a scientific point of view. Also, in this developing scientific way of thinking, yesterday Professor Upadhyay emphasized that you have to update your courses. Most of the books are written, maybe they are 10-year-old, 15-year-old. If you develop that scientific way of thinking, the student should later be able to adapt and learn new things by themselves, right. Because I can teach a student basics and teach him or her to analyze the problem. I cannot solve all foreseeable problems in my class. Since I cannot do that, the best I can prepare him is to himself be able to look at a problem and analyze it. If I can serve that, if I can offer that in my core course, I have done my job. Now, I would like to hear from you if you want to add something, if you want to comment, or Chandra, you are welcome to if you want to comment something, if I missed out on something.
Actually, in this part, the physics, I would say physics is a universal science in some sense. It's very easy to relate what you see to physical concept and explain it. Mathematics, for the teacher of mathematics, it's important to borrow from physics. For example, when we talked about it, when I'm solving ordinary differential equation, you have to emphasize why am I going to use it, where am I going to use it. Okay, could be spring damper system, could be a continuous system. Okay, so I'm talking of differential equations in time, differential equations in space and time, which means all these things about the Sturm-Liouville problems, they become relevant to the student. And then see there, if you talk of the nature of solutions, what he said, nature of solutions is universal. It manifests in different domains the same way. If it's a wave motion, it's a wave motion. You can't stop it from happening. And if it's something which is decaying in time, well, it has to decay in time, whether it's heat transfer, whether it's solid mechanics, whether it's a damped system or an undamped system. So if a teacher of mathematics can emphasize that in class, a linear algebra. The linear algebra has become essentially something which you cannot run away from as a student. Unfortunately, that's something we do very poorly in our
Mathematics
courses. We actually de-emphasize linear algebra rather than over-emphasize. Okay. Now, over there, you can actually set up a lot of beautiful, simple problems, examples from engineering, which these guys can connect with and use linear algebra. So this is what I wanted to add on.
Sure. Yeah. Now, so let's start now. When I do this, a very important course component in any course, which again I don't know whether it is universal, but certainly we see in our students, whether they are in IIT or engineering college, experimentation is missing. You see, engineering, if you look at a good engineer or a good scientist, they observe. They observe a phenomena, they may not be able to understand it right away. They analyze it and use it in a certain way. And when they use it, that's the engineering application, right. So, I have to show students that whatever physics you are learning, there is a related experiment which is also being used in engineering. And nowadays, things are so much available, even if you cannot think of a lot of experiments yourself. Although you can, I mean, trust me, you sit around and you can think of a lot of experiments because there is a lot of things going around. there is Google available, YouTube available. You type a word and that shows you an experiment, and then you make it. And these are made by easy things. That's one. Other thing doing these experiments and demonstrations does is tells the students, work with your hands. You see, this is something you can do a lot of simulation, but engineering or anything final product you make, until it is field tested, until experiments is done, nothing happens, because finally the product is going to go into a person's hand and is going to be under different situations. You have to learn to do experiments. You have to just come up with experiments and see what happens. In fact, I'll show you one experiment where then I'll show how things progress, right. So, experimentation is very important in engineering students, science students, whoever. I mean, they have to learn to do things. Then you see whether whatever theory you have learned, it's okay, and if it doesn't apply in certain cases, what are the approximations. And the favorite story I have in this thing is, now this course has been removed, but when I was studying here, there was a course called Introduction to Design. This is the first time I learned why experimentation is important. So, we decided, my partner and I, we were supposed to make a project, and that time vending machine used to be a great thing, that you put a coin and something comes out. So, we decided to make a vending machine. So, what we did was, I'll just make a picture and then you will appreciate it. This was my big lesson. So, we made strips like these, okay, made them very smooth, so they are almost frictionless, put on each strip. So, suppose this is a strip, put on each strip 2 wires, and when the coin went in, it connected with 2 wires. So, current started flowing, and then that current we put in an electromagnet that opened a valve and the water came out. So, we calculate the time, and exactly in 1 rupee, if you wanted half a liter, we gave that slope and half a liter water was supposed to come out. Everything was fine. We made everything, then we did the experiment and we put the coin in, and boom, the water kept coming out. What went wrong was, and again this is through experimentation.
Coin doesn't move it. Due to coin didn't move.
No, obviously it didn't move, but why?
Because you didn't.
No, that we had done already. Time वहीं सब calculate कर लिया था, it was matching. What happened? What we could not see, and that's why is the moment the current flew, there was a lot of magnetic field that held the coin right there. Okay. So, what we did now, our project evaluation was there. So, we took a coin, made a hole, put a the door out here, and then we kept pulling the thing, and the instructor in charge said that, oh, now I need only a particular coin, right. But he appreciated the effort, and we said this very honestly, and he said, no, this is, you have learned what the essence of design, that you have to experiment. So, you have to, through all this, teach whatever science you are doing. If you want to relate it to engineering, please find applications, and along the way you can also do some fun experiments. So, class becomes exciting, but then you keep relating. In the back of your mind as a teacher, as a driver of the class, it is clear where you are going, right. Students, so what I am now going to do is take a few fundamental principles, right, and try to tell them how to demonstrate them, how to relate them to engineering problems. Okay? All right. So, now let's begin one by one. I will start from mechanics, go all the way up to electromagnetic theory, okay, and along the way we will also do some fun stuff. And this is something it is fun, but at the same time when you are doing it in the class, you have to keep explaining the principles behind it and keep relating it. Okay? So just to start and have fun, let me call one of you. Why don't you just come here? You, anybody? Yeah, you come here. Just stand here. All right. Demonstrate Newton's third law. I don't want you to move. Demonstrate. खड़े खड़े मतलब कोई छूना होना नहीं है, जो आपके पास हो उसी करिए आप. Anybody wants to try? Come up with an idea. Just standing at your place. No words. Demonstrate. Demonstrate. Every action has a reaction. Yes, that's Newton's third law. Demonstrate it. इधर उधर कुछ नहीं छूना है ना. You see, so you can make the class exciting. Now I have given you a challenge. It's a very small thing. Newton's third law, you have heard about it from 9th grade onward. Demonstrate it. It's supposed to be fun, huh? So don't think it's a criticism or it's, a reflection on your ability. I mean, I've thought about it, that's why I'm asking you. You've not thought about it. हाँ बताइए. आओ. दूसरे को नहीं बोलोगे. Engineering is doing things yourself. आओ. No, आओ ना फिर बताओ. No, he doesn't understand. I don't understand what you mean. Do it. हाँ बताइए. जंप करिए. जंप कर गए तो क्या हो गया. कहाँ न्यूटन थर्ड लॉ.
I'm putting force, so
नो एक्सप्लेन तो करना ही नहीं है, दिखाना है. Do you mind if I ask you to take off your belt? खोलो. You don't mind, right? And I'll just show it to you. करो ऐसे रखो. Stand on it. Stand on it. अब वो जंप वाला ही है. Pull yourself up with the belt. दोनों तरफ पकड़ो. अपने को खींचो ऊपर. क्यों नहीं उठा पा रहे हो. बताओ क्यों नहीं उठा पा रहे हो. That's Newton's third law. Your action is creating a reaction and you just get pulled down. Right? Jump वाला ही है, but jump में you end up jumping. So I didn't have to say anything. I'll just call a student and say do this. Any questions on this? You can try it yourself. Right? आपकी बेल्ट गंदी तो नहीं करवाई. Okay, now I'll let me just go back to thank you. Let me see. I'll do one by one, right? As things keep coming, these are talks I've given over the years. So I'll just now what I want you to do is I want it to be participatory, all right? And I'll keep connecting. Here's a table, right? Turntable that can turn freely. All right? Where are my glasses? Now, wait a minute. What I want you to do, somebody should come here and demonstrate using this two things. Vector nature of angular. Does everybody know angular momentum? Yes? And we always say it's a vector, right? R cross P. Can you show the vector nature of this? I'll give you this, I'll give you this wheel. I want you to connect this and show that angular momentum is a vector. I am explaining a concept. Again, experimentation is important. I say R cross P and people say forget it, what do you mean? Just because you put an arrow on top, it's a vector. I want a volunteer. आओ भैया, मैं धक्का नहीं दूंगा किसी को, गिराऊंगा भी नहीं. कौन आएंगे? And I am a great believer in beti bachao beti padhao. So ladies have to participate. They always kind of पीछे रह जाती हैं. आइए आप आइए. And there was another. You are a physics teacher, right? Okay. I want another lady volunteer with her. आजो. So now what does a vector do if I change the direction? Does it change? Yes. So what we will do is you stand here. हाँ, इसके ऊपर खड़े होइए. हाँ, नहीं गिरेंगे नहीं. आप जरा पकड़ने को तैयार रहेगा अगर. Maybe let's go the other way. She is easier to hold. हाँ, you stand here. Okay, now you stand here. Yeah. Now I'll give it to you, right? By giving it a rotation. You got to hold this. Hold करिए दोनों हाथ से गिरेंगे नहीं. हाँ. Now you see she is standing here, right? If I change the vector direction, how do you change the vector direction? Flip it. Flip it. उल्टा करिए. You see she starts moving. Right? So what did we do? Thank you. What did we do? there was a direction in one direction, and when we change the direction, something changed, the vector changed. I also know from conservation of angular momentum it cannot happen. So, she started moving. I have just shown that there is direction associated. If you change the direction, angular momentum changes, right? अच्छा, I want you to do one more thing. अब आप खड़े हो जाइए. तो इन्होंने गिरने नहीं दिया था आपको, आप भी हाँ hold this, हाँ नहीं रुक जाइए आप, हाँ you can just leave. Now what I like you to do is नहीं अभी खड़े हो जाइए ठीक से, ठीक है, हाँ ऊपर थोड़ा करिए, इसको एक राउंड दीजिए क्योंकि देखिए क्या होता है. See what happened? She started moving, right? Stop it now, stop it, and she'll stop. Do it again. जोर से दीजिए भाई, आप तो कब खाना वाना नहीं खाया सुबह. She starts moving again. Now I want a guy with a strength who has had that extra breakfast thing in the morning. अच्छा हाँ भाई किसने आइए, हाँ कम आप बैठ जाइए, थैंक यू. ओके हाँ कम स्टैंड हियर. इसको पकड़िए ऊपर से और इसको जोर से धक्का दीजिए, दूसरी तरफ घुमाइए. हाँ हाँ बिल्कुल. See, he starts moving, right? You hold this now. Stop it now. रुक गए. उल्टा धक्का दीजिए. उल्टे हाथ से पकड़ लीजिए. इससे पकड़ लीजिए, उल्टा दे दीजिए. हाँ उससे उधर को दे दीजिए. रुक जाए. Yeah. It starts going the other way, right? So what does it teach me? It's conservation of angular momentum. There was no, thank you very much. There was no external torque, right? If there was no external torque, the angular momentum has to be conserved, and therefore the moment he did this, he started moving the other way so that the net angular momentum remains 0. So that's very good. Everything is fine. Now let us look at this picture. Okay, I'll make it bigger, right? And now I want you to explain to me. I want you see this helicopter, right? On the basis of this, I want you to explain to me why that rear rotor is there. Now I am connecting conservation of angular momentum. I have demonstrated it, right? And through this, I want you to explain the rear rotor. You see, this helicopter has this big rotor and a rear rotor, right? Similarly, if I go to the next page, there is a different design of helicopter where they have 2 rotors. You see that? Why? Change the direction of what? मतलब अगर ऐसे चलना है, टर्न करना है, okay? Other, to make it stationary when it's hovering, huh? Okay. What else? Now I want another volunteer, huh?
Clockwise and anti-clockwise torque management.
How?
If one blade is rotating clockwise, another is rotating.
So why do I need that? I want you to explain it through on the basis of this experiment that we just shown. I want another volunteer. आइए कोई volunteer आइए भाई. कहाँ है volunteer? कोई आइए. आइए. नहीं आप तो हो गया. एक जना कोई और. You have to participate, otherwise there is no fun. Imagine you are doing it in the class and nobody shows up. How would you feel? हाँ come. अरे वो बन रही है कोई वो नहीं कुछ नहीं होगा, वो हेलीकॉप्टर में नहीं जा रहे हैं आप. So again I want you to stand here. Imagine you are a helicopter. This is your upper wing, rotor. खड़े होइए उसमें, नहीं खड़े होइए उसके ऊपर. हाँ अब हेलीकॉप्टर स्टार्ट करिए. हाँ मतलब चाहिए. See the helicopter starts rotating the other way, and I don't want that motion to take place. That's why the rear rotor. Okay, and similarly instead of 1, if I have 2, thank you very much. Is that what you meant when you said earlier? Yes. Okay. So rear rotor provides that counter torque. If I start the helicopter, if I don't have that rear rotor, it will start spinning. It will go out of control. if there is a helicopter which is flying, right, in army, in warfare thing, you shoot the rear rotor, helicopter is gone, because the balance is gone. And in the next page, right, in the next page, now instead of one wheel, you have two wheels, two rotors, one going the other way. Then you are balancing the torque. So, either you should have a rear rotor or you should have two wheels, then you are doing all right. Is that okay? Okay. Now, again on the principle of conservation of angular momentum, I have to show something, and I got these for men, these for women. Lighter ones, pink ones for women and blue ones for boys. Okay. Again, some more, Betty. Aye. And I want another girl who can push her. Not push, but you know. खड़े होइए. Aye. Okay, you come here. Please help her stand on this. Okay? Okay. You hold these and spread your arms. Now you just give her a push so that she rotates. Take your arms in. What happens? बाहर ले जाइए फिर बाहर ले जाइए. You slow down. Do you feel it? Do it the other way. अब उनको करवाइए. हेल्प करिए भाई उनको. Do the same thing with her. Okay, spread your arms. Just give her a push so that she just rotates around. Yeah, take that thing in. You see the difference? And take it out again, and you slow down, right? Okay, रुक जाइए. Anybody else who would like to do it among the girls? इधर से आइए भाई. आप लोग चुपचाप बैठे हुए हैं. No, girls. बेटी पढ़ाओ, बेटी बढ़ाओ, बेटी बचाओ. Another बेटी. One more. करिए, same thing. You want the helicopter thing or this thing? Which one do you want? This thing, okay. Stand here. Okay, help her please. Spread your arms, and I'm going to push you. Now take the arms in. You see the difference? That's again I explained that when these are out, mr square, moment of inertia is very high. You take them in, it becomes small, but angular momentum has to conserve. Up, आप भी करिए. You cannot just leave her to fall down. Now you see, I'll just want to, if you observe, again it is not a commentary on you. She has a smaller frame than hers, right? So the difference would be less. The moment of inertia ratio change would be less in her case, right? चलिए घुमाइए भाई इनको. कैसे ऐसे घुमा रहे हैं? घुमाइए. अंदर ले जाइए. हाथ सीधे कर लीजिए. जहाँ तेज हो एकदम फैला दीजिए फिर से हाथ. ये. You feel the difference? Yes. So you see, I have explained the concept that moment of inertia depends on how far the masses are from the axis of rotation. Right? You bring them in, moment of inertia goes down, angular momentum goes up. Now boys, उनके लिए बड़े वाले हैं. आइए भाई, आइए. एक इधर से आइए. आपको पतले ये वाले चाहिए, हल्के वाले चाहिए? आइए. So you can just pull your arms in like this. You don't have to do that, right? फैलाइए. आराम से. मैं इसीलिए बड़ा सिमेट्रिकली कर रहा हूँ. हाँ, अंदर करिए आर्म्स. आइए. हाथ फैलाइए. अंदर ले जाइए. बाहर ले जाइए फिर से. स्लो हो जाएंगे. राइट? Okay, very good. You want to see the helicopter thing again? Huh? आइए helicopter भी बनिए थोड़ा सा. I'll give you another one. This is easier to handle. His frame is small, so he'll make a good helicopter. अब दीजिए. ये देखिए. हाँ. So if I put a tail rotor out here, he'll be all right. Okay? Thank you. All right. So you see, not only I gave a concept, I immediately somebody from there said earlier related to an engineering problem. The moment you say this, you have related it to an engineering problem, right? Okay. Now I need to do another setup, which I'll do out here. Okay. Oh, now that I looked at the water bottle, I can give you one more. Let's see. Let's do this. Let us just tie this on this, right? And यहाँ पे इंटरनेट भी चलेगा ना? क्यों? Oops, थोड़ा सा भारी, इसको बांधें कैसे? नहीं, इसको थोड़ा और लंबा चाहिए सुतली. देखते हैं. I have a pair of scissors. Let me see. हाँ? नायलॉन रस्सी मेरे पास भी है क्या? लाओ लाओ जरा. I'm also a little. This room has become hot now, so I have to take off my thing. So you have to have a little patience with me, okay? It will take time to set up, but the point I am making is very important. Meantime, okay, then I'll show you something else in the meantime. Okay, now what we'll do is, you see these tracks? These are made specially. This is kind of a track, but the way we made it is it turns around. Okay, you see it turns around. Okay, and then you missed a lot of fun. It turns around. Okay, you see this? So what I'm going to do is now make this entire track. To take it around, I've just cut it in 3 pieces, but we'll assemble it. And हाँ कर दीजिए जरा सा, इसका भी समझते हैं.
तुम लोग 2 जन आ जाओ, हेल्प कर दो.
हाँ, this is participatory, so you can participate.
Volunteer, come.
ये end में है. So let's make this track, all right? इसको height करने के लिए, just to give it height, because I want something to roll on it. Okay. Okay, and then there's the last one. इधर लगा दीजिए इसको. All right. Okay. So you see this? All right. Let's remove all this so that all the junk is out. Now, what I want, now a lot of people, you should come and play around with it. Okay, what I want you to do is, I have these 4 different kinds of rollers. Alright? So, honestly, I have a little smaller one, but the bigger ones are okay. Honestly, I'd like you to come.
इसकी तुमको जरूरत है?
हाँ, इसका भी पड़ी हटा दो. I'd like you to come and honestly in your mind think about, if I leave a roller from here, which one will go all the way through all the curves. Okay? Come here and honestly tell me if what you thought was okay. Try all these 4. Who was what? Okay. So you show, you please, it is as if your class. I am doing this and this is what is going to happen and I think this is what happens and then you show the result. अब बताओ सबको बताओ ना पहले बताओ क्या होगा कौन सा रोलर आखिर तक जाएगा हाँ देख लो ठीक है काट लो पहले You show all the 4 rollers to everybody. These are different shapes. Concave lens. This is a roller which is thin in the middle, thick in the sides. You cannot see, yaar. Not like, exactly cylindrical, plain.
And this is thick in the middle, and then at the end. And this is somewhat different, which is
Okay. Now, which one do you think will? अब देख लो, तड़ लो, सब कुछ कर लो हाँ.
without trying you.
No, without trying. You have to guess. Somebody, he's saying something. आ जाओ. The last, I don't know which way he showed. I mean, I don't know. सिलेंडर देख ले रुक जाओ आने दो ये भी आ रहे हैं कुछ बता रहे हैं.
I think this will finish the.
Okay. So let's try all 4 of them. Okay. नहीं नहीं अब वो आपने बहुत एक साइड से कर दिया उसको ठीक से दीजिए और बहुत तेज धक्का मत दीजिए क्योंकि ये ट्रैक थोड़ा सा हल्का से दे देते हैं. ठीक है बाकी दिखाइए. ये तो वहीं पे गिर गया. हाँ हाँ हल्के से यार बहुत तेज मत दो फिर ये. हाँ वो वाला ये भी यहीं पे फुस हो गया. This one actually goes. Your guess was right. All right. So let's just do it carefully because that's why I made it long. Maybe the speed is coming out to be a little too high. But you see, it negotiates. It negotiates. It negotiates. It goes both ways. The other ones, right? This plain one just goes straight. It doesn't do anything. कुछ कर ही नहीं गिर जाएगा. It doesn't even turn. This one goes one way and just that's it. This one also goes one way and just conks out. Okay. So let me just make the picture. Others are welcome to do the experimentation if they want to satisfy themselves. Please feel free to come and do it. Then we'll analyze it. Aajo. If she is interested. So in the meantime, I'll just show it to you while she is experimenting. I don't mean to neglect you, but this is the track. This is a kind of track. Oi. Wait. I have a few tricks up my sleeve. If she claims the plain one goes, try this one. This is a little smaller. You see, that was too big for the track. It does not turn. You see, if you notice, it does not turn. No, अभी छोटे वाले हैं. छोटे वाले try करो. If I'm fooled, I have a few tricks up my sleeve. It does not even turn. You see, it just goes one way. It also just goes one way. You see that? And try the last one. It will go both ways. You see, it's turning both ways.
उस वाले को फिर से चलाओ.
हाँ.
You see, one observation does not prove a point.
Yeah.
You have to have multiple observations.
तो लंबा है ना थोड़ा, तो वो निकल नहीं पा रहा है। अब देखो ये, okay, it doesn't turn. This one turns. This was even smaller, but it made the journey all the way through. You see that?
That was coincidence.
That was just a coincidence. Also because it's, you see, the size is much bigger than the track's width. So it did not just go straight, it was just put this way. But none of these four, the other two turned one way, this turned both ways, right? So what we have learned, please, anybody else who wants to do something? So what we have done is, we have taken this cylinder, plain cylinder, and a cylinder which kind of to fool people that, oh, it will cover the thing both ways, right? It is this one that goes through. Why? Yes.
Sir, when a curve comes and cylinder slides in either in one way and the radius changes.
The radius changes, right? Where is it used? Railway. So I'll show you that. Okay, it's an engineering application. Okay, so now I'm going to show you. Page down. यार इसको कागज पे चलाना है. See, now the railways do not have a differential. Now when a car turns, the outer wheel is going on a bigger radius. It needs to cover more distance. So if you have noticed in a truck particularly, the rear axle has something very thick in the middle. That's a differential gear. It adjusts the speed of the outer and the inner wheel. Railways don't have that. In any case, railways it will be very difficult to maintain also, right? So they have something else, and this is the trick they use. So this is really an engineering marvel. इसका वॉल्यूम क्यों नहीं आ रहा है? वॉल्यूम भी देख लो थोड़ा. तो ऑडियो नहीं आ रहा है इसमें. अच्छा, लैपटॉप का तो है, उसको चला देता हूँ. इसमें देखो ऑडियो कहाँ से आ रहा है, इसमें कहाँ से आएगा सेटअप.
यहाँ पे सर, यहाँ से इस पे सर आ नहीं रहा लैपटॉप वाला ऑडियो.
कहाँ से?
राइट वाला जो है,
ये
राइट वाला आइकन है सर.
फुल है. Anyway, the idea will be all right. Anyway, ठीक है. But idea will be clear. You don't need the. Now you see, this is a train going, and this is a Russian film. But I want to show you something more after this. Again, how do you keep experimenting? So now here's a track in which the train is supposed to turn. Right now, you see, it shows the two radii, and when a wheel goes, now you see, this is precisely that roller that we used. The middle part is removed, right? Now when the wheel goes, it's supposed to okay, now it will start moving. Now you see, if it is, because it's turning to the right, the left wheel has gone up on the track, and therefore its radii of curvature becomes larger automatically. With the same omega, right, the outer wheel now goes faster. And similarly, now when you go the other way, right, the wheel on the outer side will always have a higher radius, and therefore it will negotiate curves both ways. Now, somebody when making railways must have observed this. Just from observation, they made a railway track and a railway wheel. It's a fantastic innovation. If you really think about it a bit, you don't need a differential gear, nothing. Just by giving a slight slope, you're making something which turns on the tracks. And that's the engineering application you see of it. It's a pure kinematic effect, V equals omega r, and we are making use of that, right? So, this is now the point I am trying to make is you make a demo, you also have things available on the YouTube that can immediately connect, right. Now, a design problem, again if you look at this, other place which will become, so is it clear why that thing which was going like this, why it is going? Because when it turns, the higher radius comes on the outer side, and therefore, that part moves faster, okay. And it's a fantastic innovation, all right. Now, a similar design problem for you and for other engineering students would be, if you look at the rickshaw cannot have a differential, it does not have a differential, right. And therefore, when the rickshaw wala turns, right, what will happen? One of the wheels will skid, the wear and tear will go out, will be higher, right. Or there is another design that is used in Thailand, is they make one of the wheels free. Is that okay? So, one wheel is connected to the pedal, the other wheel is free, so that it adjusts its speed when you go around, but it makes it little unstable, okay. It can topple. That is a fantastic design problem for you, for the engineering students. There is a very simple thing, but you apply engineering. Now, we will go to the slightly higher level on this. Slightly higher level is, and I am going to write this here on the YouTube, is okay. Let us write now. I am going to search how bullet train. Now, you see, if you are doing the same thing, does it apply everywhere? And let us see that. Okay, bullet train. This is, there is a fantastic video that comes. Okay. Bullet train track, Japanese bullet train, Skillsman documentary English, how to flip this. Let us see, this may be the one. No, this is not the one, but I am surprised why the thing is not coming. I will search for it. In any one sec. Bullet train turn wheel design. And this shows why, this will show you why experimentation, this is the one. I do not know why sound is not coming, but let us see. But I will explain it to you. Now, this is a bullet train, one would expect that bullet train would do the same thing, right. You put the thing on the track, I wish the sound had come. Now, we will try exactly the same thing, that we put the wheels with this round and you will see what happens if you go at a higher speed. या जरा सा साउंड अगर लगा दो तो बहुत अच्छा होगा. लैपटॉप का साउंड तो आ रहा है, लेकिन लैपटॉप में भी नहीं आ रहा, पता नहीं क्यों. मैं घर पे तो सब चला के देखा था कल रात को. कुछ कर रहे हैं, देखो आया. अच्छा, वो हेडफोन वाले में था. ओके. You see now.
Round. Round is good in a wheel, but it's the part that touches the track here that makes contact. That is absolutely critical. Without the help of a medieval clock, a high-speed train could simply throw itself off the rails. No need to take my word for it, because I brought my very own.
Now you see why experimentation is important. He is doing the experiment with the same kind of wheels that we use on the railway track, but he is doing it on a straight track now, and he will show something very important.
It doesn't even have its own power, but that doesn't matter, because I've got a powerful winch to drag it along this dead straight piece of track that speeds up to 50 miles an hour. Unfortunately, Hammond railways don't stretch to basic amenities like seats. That's one of the reasons why I won't be riding on my carriage. The other reason is, well, it doesn't have any brakes. I did say it was basic. It'll be brought to a complete and probably quite sudden halt by that barrier down there. On the plus side, this does have everything we need to show just what high-speed train engineers are up against. Namely, we've fitted it with these train-style wheels. They're exaggerated, yes, but just like real train wheels, they're conical, angled where they rest on the track. They might look pretty odd, but according to Paul Allen, an expert in wheel dynamics, they'll show clearly what happens to real trains travelling at speed. Finally, Hammond Rail is offering a feature never before seen on trains: basketballs on corners. They'll show how the carriage moves. He's revving his V8 muscle car from 1970s. Here he goes. As it speeds down the track at about 40 miles an hour, the carriage starts rocking from side to side. It's called hunting oscillation. Oh, we see that. Is that why the top of these posts are moving side to side?
Yeah, you can see it hunting a bit now.
That's not gone at all well for it, has it? That's a bad thing. The kind of thing you need to avoid.
So after that, the design of bullet train comes. The point I want to make has been made, and the point is,
Railed on a straight track, and the repeated sideways movement can also.
point is even with the wheels, conventional design of wheels, if you went to high speed, the whole thing became unstable, right? So this is what engineering is all about: experimentation and finding out. So the simple track experiment showed you how the wheel design should be. Then I show you, if you want to go to high speed, even this becomes that hunting oscillation. It has instability moving side by side. You have to come up with a new design. This is how in a core course you can actually excite students, right? Is the point well made? Understood? And you see, these things are available. I am just pulling them out right in front of you, right? Okay. Now, furthermore, now so this part is done. Okay. Now you see, again, this experiment is very easy to make. You just took some aluminum things, just put them on the track, made them like this, and for this thing, right? And it's done. Now what I want to show you is how you can, if you don't have the machines and all that, you can even make it very nicely at home. And here it is. One second. You want to make them at home or just in the class quickly? And I did that in the class just for the, sake of showing. And here you go. Okay. Train tracks, how trains go around the corner. Here it is. You just take two pipes, right, and the glasses at home. We all have those, right? The throwaway glasses, plastic glasses. You can just add them together and make these two kinds of wheels, right? Just in the class, and you're done. It's so easy to do. So that is the point yesterday he was also making, that these things are very easy to make, but they make the point very nicely. Okay, you can just show the train turning through this. Now, I am going to change tracks and let me see. I am going to show you something about the stability. Have you all heard of gyroscope? Yeah, what does it do?
Measures the rotation from certain axis.
What else? So, I want to show you something what gyroscope does. The light de dijiye please. What a gyroscope does is actually gyroscope, and just want you to, I had the bigger gyroscope, and that's the story I was telling yesterday. The stand went out, so I'll have to show you the small one, all right. And what it means is basically, and I'll give you one word for that, and then again I'll show you something very interesting. Okay, how are we doing in time? I mean, on this I can just keep going on and on and on. अच्छा, इसमें ही नहीं आ गया, ठीक है, इधर है. So 11:10 तक तो डेट शुरू करा था ना. अगला कौन है? मैथ्स में है कौन? हाँ हाँ यार, उसको थोड़ा समझना मुश्किल हो जाएगा. But I can anyway come back later and do it for them if they want. So, I am going to run this gyroscope, right, and you see it does not fall. Yeah, okay. It precesses, right. Other thing it does, and which I have made, but I am not going to do it here because is you can put the gyroscope in something called and which I will show you in a different way. Okay. अरे यार ये सब तार वार हटा दे रहा. No, I will show it to you. Something called a gimbal. Basically, you take this and put it in another frame from outside. Okay. And what you can show is that the direction of gyroscope remains unchanged. Okay. Even if you make that gimbal move around. I made a gimbal, but it's right now all stuck all around the place. But I can show it to you in another one, and that is a gyroscope from lab. This is the one. ये वाला जो दे दीजिए, इसका एक पहिया भी था, वो इसमें होगा, इसमें देखिए तो जरा. Here a gyroscope. नहीं दूसरा छोटा सा था, इसमें तो नहीं है. हाँ नहीं इधर है. I'll stick it here, all right. I'll stick it here. Okay. Now हमारे पास वो नहीं है यार, एक स्क्रू ड्राइवर.
स्क्रू ड्राइवर चाहिए क्या सर?
हाँ है तो ला दो जरा. Okay, anyway, I'll show it to you when you. So, what gyroscope means basically is stability. I'll show it to you that when you put it in a gimbal, it defines a direction for you. Okay, and where can it be used? It is used in rockets. Okay, this was a big technology that was used in rockets when in V2 rockets to start with. Do you know where the V2 rockets were used? So, this is how a gyroscope guides a rocket, and I will show it to you. Again, engineering application of something which is nice to do. Okay. Then I can show this to you.
Of the methods used to stabilize a rocket, if you like, and keep it on its trajectory, there's one that most people I think are familiar with, and that's the stick on a bottle rocket like this.
By the way, on this you can make a very nice problem. Holding the stick on your hand, and how long does it take to come down?
Counterbalancing stick is all very well for a firework, but
I'll leave that as a challenge for you to make a problem of the stability of the stick on your hand.
real rocket, something that's far more dynamic and able to cope with the changes and aerodynamic
Oh, nahi, 2D अच्छा.
movement, wind
Thanks.
on the rocket, and things like that. It needs to be a principle as dynamic as I'm trying to demonstrate here with this out of balance broom, trying to keep it upright. Just take a look at this V2 archive footage. The V2 is shown hanging in the air over the firing point, probably because the turbo pump is under running. So instead of the motor delivering 25 tons of thrust, it's probably only delivering somewhere between 12 and 13 tons. And the only reason the rocket is climbing at all is because of its use of propellant. But you'll notice that something is...
And this. See how stable the rocket is. That's what he's saying. It's just standing straight, right? And that's where the gyros were used. And now we have electronic gyros. Nonetheless, this is a mechanical gyro. Yeah.
These gyroscopes are the brains of the rocket. They are in universal mountings. Electrical pickups measure the movements of the gyroscope and translate these movements to the carbon vanes and the trimmers in the tail unit. These vanes and trimmers direct the rocket both in bearing and elevation along its trajectory and prevent any deviation from its planned course. The four vanes are in the jet of the rocket, and there is a trimmer on each of the four fins. This mock-up represents the inside of the control compartment in the rocket. In the background is a skeleton tail unit, with the vanes and trimmers in position. The control compartment moves, the gyroscopes move in their mountings, and these movements are conveyed through electric cables in the rocket to corresponding servo motors in the tail unit. There is a servo motor for each carbon vane and trimmer. The servo motors move the vanes and the trimmers to counteract the original movement of the control compartment.
So it brings it back. There's a feedback mechanism.
This gyroscope controls the elevation of the rocket by moving a pair of the carbon vanes, thus turning the rocket from the vertical over to an angle of 43 degrees. The other gyroscope controls the direction of the rocket by the movement of this pair of vanes.
Let's take a closer look then at a real gyro platform from a rocket. Here's one from the German V2 ballistic missile.
And by the way, that was
It's fairly well
an engineering marvel that German V2 rockets were so precise. And that is one technology that Americans wanted when the World War II ended.
Gyro platform that really lets us
So he'll show you how this stability comes. I actually made that. This is right now.
in trim. Is this
I just want to show you
some of
how.
its properties and see if we can pick up some of the
This is the same gyro I showed you.
this device might be able to control a rocket. Just going to give the string a good pull, get the rotor going. There's the first thing it seems to be able to do really rather well is balance itself. I'm going to take it off here, put it on its little stand.
This means stability. Gyro means stability.
As I move that around, there's
Nothing happens.
I can even pick that up, that rope here.
He'll balance it on the rope. That's okay, but
A little trick here with the gyro.
more important thing is how he.
Cover it, notch at the tip there.
So
And
this
you can see
I can skip.
It does a pretty good job of stabilizing itself.
I could have shown that to
Very
you,
good
right?
demonstration of the preservation of angular momentum. It's beginning to process a little bit now, but I still don't think it's absolutely obvious what it is about the gyro that's going to allow us to control a vehicle like a rocket. So I'm going to try to show you next that's going to let us actually control a rocket.
So he's going to make a gimbal. This is basically outside frame.
Okay, so there's what we've made, and it's a gimbal unit, so that I can now put the gyro into that inner gimbal frame. It's not exactly a wonderful piece of engineering. It's not really going to win me any prizes, I don't think, but I think it will do for our wonderful demonstration. I don't think, but I think you get the idea. The gyro is now free to move at any angle. And this is going to give us a much better chance to show you one of the principles of the gyro. That got plenty of rotation on there. There it is, operating. Now watch what happens as I move it around.
See, nothing happens. The gyro direction
See
remains
that
the fixed.
gyro is actually retaining its position in the space. It'll start to be overcome by the friction of the bearings as I move it around.
That's the whole idea.
It won't be quite so
Okay,
motion
so
being induced in the gyro as I.
you take a gyro, show its stability, and show the rocket. And that's. I mean, a lot of people who are in space sciences try to make a good gyro. It has to have a very, very high RPM and be stable, not lose energy, right? So that's I mean, he would be able to tell more. This is supposed to be the heart of the rocket to stabilize it. Okay, so that's the mechanics part. Now let me see what other I have, and I have very little time, right? So let me see. This idea is this I could have shown. Now let's see. Other thing I am going to leave for you. Now, I also wanted to show you the effect of surface tension. Now, I am moving away from mechanics, and I will come to now the electromagnetic part a bit. Okay. And let me see what I have here. एक बैग और था ये वाला, इसमें होगा मेरे. चलो लाइट, अब तो लाइट दे दो. Petri dish. Okay, I have a few things here. So my I had something more, but I can't show you that now, lack of time, but nonetheless here. Now, you see a concept which is, इसको जरा ऊपर कर दीजिए. नहीं स्क्रीन को रहने दीजिए, ये ऑन चाहिए मेरे को, इसको बंद. Now, what I want to show you, there is a concept, right? Again, this is for the fun part, called the surface tension, right? And a lot of people have a big difficulty understanding surface tension. Surface tension also plays a very important role in one particular engineering application I am going to talk about. Okay. So, here it is. Now, let us put some water on it, right. Okay. Now, this, what do you understand by surface tension? It is something on the surface. We always say there is a sheet, right, and if you take a line, there is kind of force. And what happens if you take soap? What happens to the surface tension? Huh? It becomes? No, it becomes smaller. So, water spreads much more. That is why when you put soap, water spreads much more, goes into the clothes, cleans out the dirt. All right. So, we always think of surface tension as something force per unit length of a line on the surface. How do I show it? So, I am going to show it to you. All right. What I will do is, I have here, what is this? Let me just see, huh? This is, yeah. So, I am going to sprinkle some black pepper on this water. Okay. You see this? And now, what I am going to do is put a drop of soap solution in the middle. See what happened? Now, this immediately tells you that wherever the soap solution was, surface tension was less. Therefore, if I took that line that separated the water and the soap solution surface, which way would be the force? Towards the water. And you see the thing just spread, right. Another way to explain this is that surface tension is same as energy per unit area. If I have something which has less energy per unit area, the overall energy will be less if that has more area, and that is precisely what happened. right. So, this is a beautiful way of showing it. I had this water plant and all that. I would have actually made a boat using a surface tension thing, but that is maybe for some other time, because I am running out of time. Now, why is this important, these fluid properties? I want to show you another property of fluids. Okay, could you just switch that off, please? And that is, so something called the coffee ring effect. If you notice, if you ever get, the dal comes on your shirt, maybe a drop, right, when it dries, it is not uniform spot, there is always a line on the side, right. So, I will just show it to you that there is this. What I did is, I took this coffee thing and put it on a plate at home, right. So, as the drop dried, you see what happens, on the side it is much thicker, the material comes to the sides. I took the holy color, right, made a drop and let it dry, again the same thing happened. What is known as coffee ring effect. Okay. This is a well known coffee ring effect. That is, if there is a drop of coffee, and notice in this that the side lines were all nailed, so the side where the boundary was not moving. So, if the boundary does not move, all the material comes to the boundary, okay, and it creates problems. Where do you think it could create problems in engineering application? Inkjet printer, when you put the ink drop, when it dries, it can have the same effect, and it does. Okay. So, that ink drop, when you read it, it will not be uniform, it will be thicker on the sides. You have an engineering problem at hand. You cannot print uniformly with an inkjet printer unless you overcome this problem. All right. So, there is a lot of research on this, and there are other effects. Now, first I have to understand why this happens. This is again, when you are talking engineering, you can talk to a lot of students and talk about, so I do this when I teach electrostatics. In electrostatics, there is something called the Laplace's equation for electrostatic potential, del square phi equals 0. We all teach that. Not only it occurs in electrostatics, it occurs as a beautiful equation in mathematics, everywhere. Now, let us motivate. If you look at particle diffusion, there also in a steady state, the density distribution or distribution of particles satisfies the same equation, del square rho equals 0. All right. If you look at thermal diffusion, right, if heat is going from somewhere to somewhere, in a steady state, temperature satisfies the same equation, del square T equals 0, right. So, what does it mean? If I have solved it for, say, a temperature distribution, I have solved it for my electrostatics problem, I have solved it for my particle diffusion problem, right. I am connecting, right. And so, they are all related, and I will show it to you. So, electrostatics, del square phi equals 0, electric field is gradient of potential, flow of heat is gradient of temperature, flow of particles is gradient of diffusion. So, electric field currents corresponds to heat current or particle current. Now, let us see what happens. If you look at potato fries, right, this is a picture taken at home, you see they become darker at the edges, right. Similarly, if I look at ice cream block, it melts at the corners, right. And where do I use that? If you look at the electric field lines near the lightning conductors are very sharp. The electric field lines are very sharp near the lightning conductors. So, what happens is when the lightning strikes, it strikes right at that corner, because that is where the electric field is. Now, as I said earlier, electric field is same as thermal current, is same as particle current, right. So, if electric field lines are sharpest near the edge, where would the diffusion current be sharpest? Maximum near the edges, maximum evaporation of water takes place near the edges. Therefore, all these potato fries become dark near the edges first, right. Similarly, heat current would be maximum near the edges of the ice cream cube. So, maximum heat goes out or goes into the ice cream from the edges, and therefore, ice cream melts near the edges first, right. All the edges become very smooth, they are all connected, and it is the same effect that gives you coffee ring. If you look at this drop is like, you know, we have shown a drop. Now, maximum evaporation of water would take place from near the edges. That is why the potato fries become, you know, the dark near the edges. And when water goes from the edges, what will happen? Rest of the drop, the water will come there, and it will bring all the material with it. If it brings all the material, what you have at drying is that coffee ring. Okay, how do I control this? There are tons and tons of papers on this. You control it by playing with the surface tension and the water flow of the thing. Okay. Surface tension is controlled by something called the Marangoni effect, but anyway, that is a different thing. Now, this I wanted to show you this. So, this was the wrong way of using it, where because of this your drops are becoming non-uniform. This is done by Professor Monica Katiyar in our MSc department. She used it the other way. She said, if things deposit on the sides, right, and if I start depositing things, always there will be an edge on the side and it will make kind of cup. So, I can deposit different drops using that cup, and she made a device out of it. Okay. So, again you see an effect which is related to electrostatics, thermal diffusion, particle diffusion being used in an engineering application. And this is how you can actually, you do not have to go into the details, you can just connect and excite students about why this core science that they are doing, how it is related to courses later, how it is related to engineering problems. All right. So, now let us see what else do I have. So, this is how they did it. These are different papers that came. Let me see if I have something else. Yeah, this is something I had, and I do not think I have a movie, and I can maybe show it to you. Now, this edge thing you can show, I had brought it, and but I can give it to you, but I can just let you know. If you take a piece of paper, all right, piece of paper, put some potassium permanganate on one side, fold it and dip it in water, you will see maximum potassium permanganate will go from the edge. Sharper the edge you make, more will be going from there. That is basically an effect of diffusion taking place from the edge. Okay. That is the one I have, and I think I will stop here. It is 11:30. Hopefully, I have given you a flavor of doing science, teaching it, but connecting it with engineering problems. There are a lot of interesting problems. They are available on YouTube. You can make them easily, and you can use a combination that hopefully will excite students, and also keep the science core courses relevant for them. Okay. Thank you very much.